Good afternoon, all. Very warm welcome to our first official webinar. So I am just excited to see all of you after so long time. As you may know, today's topic is a formal logic of cellular automata. This is a joint work by Professor Sukanta and Professor Mihir Kumar Chakraborty, our sir. And this was presented in Automata 2020. So kind of this is an extension of automatic talk, and I'm expecting an interactive session with all of you. So I now request Professor Das to start the seminar. Over to you, sir.
Uh, Welcome everybody, and thanks also to everybody, especially to Kamalika, for arranging this talk. This talk I have presented in last Monday in Automata. So same talk I'm going to present here. These are work on formal logic of cell automata. This work is done by myself, Sukanta and Mirke Chakraborty. So, so what is the objective of this work? So objective is development of a system of formal logic, and its target is to modeling of one-dimensional binary cell automata. So our primary target is to develop a formal logic, uh, keeping an eye to the binary cell automata. Now, what is the logic? We know the logic is a pair, L and turnstile, where L is a set of sentences called language, and turnstile is a consequence relation. And members of L, we normally call them whole form formulas. And the question is how to get this L, the language. To get the language, we need an alphabet sigma, and as usual, we need a set of formation rules that work on the sigma. In this way, we can get an L. And how to get this consequence relation or turnstile? Generally, it's the binary relation from a power state of L to L. Uh, However, one way to get this consequence relation is called natural deduction. Normally, we use axioms and rules to define this, the consequence relation. But in case of natural deduction, we use only the set of rules. No axiom is used here. So in our work, we develop a logic, and we name the logic as LCA, and we use natural deduction to define the consequence relation. So a logic, it has two parts. The first is syntax. Let us, define first syntax of this LCA. From the abstract point of view, in the abstract way, I can say that we start with a set of symbols, P, and it is a finite set of symbols, P0, P1 to P n minus 1. And members of P, we call them atomic WFF. So the alphabet sigma that consists of this P0, P1, P n minus 1, and along with that, four more symbols. One is sigma, the star, two brackets. And these are formation rules. And the formation rule, it's very simple rule. And it says all atomic WFFs are WFFs. And if alpha is a WFF, then bracket alpha and sigma of bracket alpha, they are WFFs. And if alpha and beta are two WFFs, then alpha star beta and alpha beta are also WFFs. And nothing else is a WFF. So the 2 and 3 are important. So we from one WFF we get the other WFF, putting the considering the other symbols of alphabet. Take an example. Consider n equal to 2, capital N equal to 2, then atomic WFFs are P0 and P1, right? And so non-atomic WFFs are, say, bracket P0, then sigma of P0, then sigma of P0, P0 star P1, P0, P1, etc., etc. So in this way, we can get a infinite number of non-atomic WFFs. So from the WFF, we can get several forms. Two special forms are there. So sigma to the power k alpha. When you get sigma to the power k alpha, we represent it. Say k times alpha is used. You can see k times sigma is used, then alpha. That's the meaning of sigma to the power k alpha. Similarly, if alpha to the power k times alpha is there, we call it alpha to the power k. So in this way, in our work, we shall use these these two special form. Let us define normal form a formula. So formula can be of any form. If the formula is of this form, so sigma to the power k1, then p1, p1 dash star, then again sigma to the power k2, then within bracket p2 star, etc., etc. And where p1 dash, p2 dash, etc., they are the atomic WFF member of P, and k1, k2, they are some greater than equal to 0, some natural numbers. Then we say the formula is in normal form. So this normal form will also be used. So, as I've said, we shall use natural reduction, and for the natural reduction, we need to define some rules. We have two set of rules. One is spatial rule. In our logic, there are four spatial rules and temporal rules. There are n, capital N temporal rules. This n is actually the number of atomic WFF, atomic formula in our logic. Apart from that, we need an equivalence relation R over L. Okay, this equivalence relation R is required to define these rules. So we shall come to this R later. Now, when these rules and equivalence relation these are given, then we can define a derivation. So in case of logic we have some derivation, and a derivation in this logic is, say, for two WFFs alpha and beta, we say alpha transtile beta. If and only if there is a sequence of WFFs, say alpha 1, alpha 2, alpha k, where alpha 1 equal to alpha and alpha k equal to beta, means I've started from alpha, then I've reached to beta, such that the condition such that alpha I is obtained from alpha I minus 1 by application of the rules of the logic. So if it is so, then we call that alpha beta is derived from alpha. So these are the spatial rules. There are four spatial rules. SR1, we call it a special rule 1, SR1. It means if in my in a formula there is alpha, bracket alpha can be replaced by sigma to the power k minus I bracket sigma I of alpha. So the meaning, so upper part can be replaced by the lower part. So SR1, where k and I, they are two natural numbers with k greater than equal to I. In case of SR2, SR2 says that alpha beta is there, alpha beta, provided that R alpha beta holds. Then from alpha beta you can write bracket alpha star bracket beta. This is about SR2. Now SR3, it says if alpha and star beta is there, then we can eliminate the star, and I can write alpha beta. And finally, SR4, there are two sub-rules. In the SR4, one, if we get alpha, bracket alpha, for bracket alpha, I can write alpha, and reverse is also true. If alpha is given, alpha is a formula, alpha is given, then from alpha, I can write bracket alpha. So these four are special rules in our logic. Out of these four, you can see that SR1, SR2, and SR4 too, there are introduction rules. Why? Because from alpha, in the alpha there was no sigma. I'm introducing sigma here. Okay. Similarly, in case of SR2, I'm introducing star here. In SR42, I'm introducing bracket. So they are called introduction rules. On the other hand, in case of SR3, we eliminate star for a formula. In SR41, we eliminate bracket. So these are called elimination rule. Okay. So these are the spatial rules, and apart from that, there are there are some temporal rules. Okay, just a minute. It's maybe it's creating a problem. Okay, so we have temporal rules. Set here I is from 0 to n minus 1. If in temporal rules, temporal rules deals with temporal rules they deal with this atomic WFF. If I find atomic WFF pi, then pi can be replaced by alpha I, where alpha I is a WFF. So pi we know it is a it is a atomic WFF. It is an atomic WFF where alpha I is an arbitrary but fixed WFF. So obviously there are capital N temporal rules. So these are the rules of a logic. So now give an abstract example of a derivation. Suppose I want to derive beta from alpha. So alpha is given. I have to test whether I can reach to beta. See here, alpha is given WFF. Then I used SR42. SR42 is I can introduce bracket. So I have introduced from alpha. I have written bracket alpha. Now I assume that bracket alpha equivalent to say beta gamma and R of beta gamma holes. Then I am writing bracket beta star bracket gamma using SR2. See, in the right hand side column, there are two columns. In the right hand side column, I am writing the rule I am applying and the action, and the formula which is transformed, which is written in the left hand side column. So from bracket alpha, I am getting bracket beta star bracket gamma in this way. Similarly, the next step, I have assumed that beta equal to beta is equivalent to say p1 dash and p1 dash, right? So then I can write say beta in upper step it was beta. Then in the next step I have written p1 dash bracket p1 dash star bracket p1 dash. So in this way, this is an abstract one, and I am saying that I am here applying the rules one by one, and doing that one I have reached to beta, right? So I have used the rules one by one. So this is an abstract derivation because we have not assumed an arbitrary alpha is assumed here. And here the intention of this example is to show that how can we derive a formula beta from a given formula alpha. So this is a derivation, and we call all derivations are not in standard form. We call a derivation is in standard form if we first use introduction rules, then we obtain normal form, then use temporal rules, and then use elimination rules. If this sequence is maintained, then we call the derivation is in standard form. However, this derivation is not in standard form. Why? Because you can see here from the top, SR42 is introduction rule, SR2 is introduction rule, SR2 is introduction rule, SR42 is introduction rule. There's no problem. So first we have used introduction rule. Okay. Then temporal rules we have used. Then after temporal rules, I'm supposed to use only elimination rules. However, I have used SR42. See, after temporal rules, there is SR3 is okay. It's elimination rule. Then SR42 is used. So temporal rule I have used an introduction rule. So it's a derivation. It's a valid derivation, but it is not a derivation in standard form. So this standard form will be effective in your work. So this derivation is not in standard form. So this is all about the syntax of our logic. Now comes to semantics. We give semantics to WFFs in the domain of D, the set of all non-empty binary strings. So this is the D set of all non-empty binary strings 0, 1, 0, 0, 0, 1, etc. everything. And we interpret the symbol sigma as a unary operator and star a binary operator. Now let us define this sigma star. What is sigma then? So let B be a binary string of length L. So how we write B? Say B0, B1, BL minus 1. Okay, we normally write the string in this fashion. Then there is a definition of this unary operator sigma. Okay, see, in case of syntax, sigma was a symbol. Here we are giving meaning to these symbols. So now we are treating the sigma as a unary operator under the definition, and it says that sigma to the power sigma 0b is equal to b, and sigma to the power kb, say k number of sigmas that there, is equal to this one, uh, bi plus 1, etc. So it's nothing but left shift operator. You can see here it was b0 b1, it is left shifted. Circularity is considered and it is left shifted. And here k, I and L, here three things are there. L is the length of string, and this is the relation. K is equivalent to I mod L. So what we understand that sigma, which was an abstract symbol, now it is here a unary operator and a shift operator. So the example is given. Okay. So now let us now define a binary relation R in D. Okay. Say two strings A and B are given, and now for two integers R and L, RAB holds if and only if R prefixes and L suffixes of two strings are equal. Take example, suppose R equal to L equal to 1. So those two strings are there within R, 0, 1, 0, 1, 1 and 0, 1, 1, 1. Here, see, in both the string, the first bit matches. First bit, the same. And last two bits are also same. So therefore, R prefixes, one prefix and one suffix, the same, equal. So this relation holds. Whereas R00 and 0011, that does not hold. Okay. So from this definition, we can get that this relation R is an equivalence relation. Why? Because it is by definition reflexive. Because R AA always true, always holds for any A in D. It is symmetric because if RAB holds, then RBA also holds for any AB in D. And transitive, it is if AB, if RAB and RBC, then also RAC. So you can test with examples that all three properties are also, it is an equivalence relation. So now, after defining this equivalence relation R, let us define this binary operator star. So binary operator star in D, so consider two binary strings, A, B. Now star is defined in this way. If RAB holds, then A star B is nothing but concatenation of these two strings. That is, first A I have written, you can see here, first I have written A, then B. So this is the concatenation operator, but this is a partial operator because for arbitrary AB, RAB does not hold, so it cannot get A star B. Take an example. Since since it holds, the last example I have seen also, R01011 and 011 holds. So 01011 star, I can get this concatenation of these two strings. Right? So we get a semantic domain. So capital D is our domain of all binary string, then sigma, then star. We call this triplet as a semantic domain. And interpretation of WFF is given in this semantic domain. And for the interpretation purpose, what we do, we define, evaluation function. So V is the evaluation function which gives valuation to the formulas of L. Let us give some value. Let us first give valuation to the atomic formulas. So the three conditions. So we give some valuation. You can give any valuation, but that valuation has to satisfy these three conditions. What are the conditions? You take any two WFF, any two atomic WFF, V of say P and P dash. then V of P is not equal to V of P dash when P not equal to P dash. So valuation that will be unique. Valuation for any V, the valuation to two formulas that will be different. So for same point is for any P and P dash. So V of P not equal to sigma to the power K for any K V of P dash. So you cannot get other valuation by shifting the other valuation. So this is the second one. And third condition is says by using the star operator, you cannot get the other one, the another get another one. So these three conditions are to be satisfied when you give some when you use some V. Take an example. Suppose P is P0, P1, P2, P3. Now we are giving valuation. Suppose consider the first one 0, 0, 1, 0, 0, 1, 0, 1, 1. Can it work? No, because 0, 1, 0 is equal to sigma of 0, 1, 0. Means one is a left shift of another. So this first one cannot be valuation. Similarly, 0, 0, 0, 0, 1, 0, 0, 1 cannot work because 0, 0 is nothing but 0 star 0. However, if I use 0 and 0, 1, 0, 0, 1, 0, 1, 1 can be a valuation to P. Now we extend this V, the valuation function for the non-atomic WFFs. And this is the way V of is very simple one, 1, 2, 3, 4. So V of alpha bracket alpha is bracket of V alpha. V of bracket of sigma alpha is sigma of V alpha. V of alpha star beta is equal to V of alpha star V of beta, and V alpha beta is equal to V alpha V beta. And we can take an exercise to get V alpha. So alpha equal to this. A formula I have arbitrarily taken a formula P1 star P1. You can see this formula and assume that V of P1 is 0, 1, V of P2 is 0, and V of P3 is 0, 0, 1. And you can take the exercise, find V alpha. Well, let me do that one. Here V of alpha is equal to, just I have put V of alpha, so V of the whole formula. Then I have applied V. In this way, I can get V of P1 star V of P2, again sigma cube V of P2 in this way. And apply systematically. If I apply this P1, P2, V of P1, V of P2, I can get this one. And finally, I reach to 0, 1, V of alpha is equal to 0, 1, 0, 1, 0, 0, 0, 1. So it means when I can put some valuation to the atomic WFF, okay, using that valuation, I can get the valuation of non-atomic WFFs. So in case of syntax, we have seen the syntactic derivation. Now come to the semantic derivation. Well, so here semantic derivation means from V alpha, I want to reach to V beta. Okay, so already to get this one, we have already interpreted the formulas. Additionally, we have to interpret the rules. Rules we have defined in our syntax. So in semantic domain, we have to interpret the rules. So they're very simple. I have given one example. So if you take SR1, SR1 means from the string V alpha is a string, no? When I put V of something alpha, then it becomes a binary string. So SR1, it was from alpha, I can get alpha to the power k minus I and alpha to the power I alpha. So here I put V in front of them. So from the string V alpha, the string V of sigma to the power k minus I, sigma to the power I alpha can be obtained. And where as usual, k is the length of V alpha. In the previous case, in a syntax, we have said k is a natural, just natural number. Here I am saying, specifying k is the length of V alpha. So V alpha is a binary string and k is its length, and I is equal to k. So in this way, we can interpret all the rules which we have defined in our syntax. Now, when we have interpreted that, then interpret the rules, then we can get some semantic derivation. For that one, we can show that semantic derivation with some example. Take this example. So assume that VP1, say P1 is 0, VP2 is 01, VP3 is 001. And our V alpha 01, 01, 00, 01, and V beta is so 401, then 50. And to see, we have to check whether from V alpha we can reach to V beta. See, in our logic, SR1, SR2, SR3, SR4, they are very fixed. But because of temporal rules, I know P0, P1. Here I have said P0, P1, P3, etc. But alpha 0, alpha 1, alpha 3, they are not specified. So therefore, when we take an example, we have to specify this alpha 0. So we have alphas in fact. So here we have redefined this, the temporal rules in semantic domain. So TR1, it is 0 to 01. Means if I get 0, that will be replaced by 01. TR2, if it is 01, that will be replaced by 00. And TR3, if 001 is there, that will be replaced by 0010 in this way. Now considering these things, we can get a derivation, semantic derivation. This is semantic derivation. Suppose, as I've said, this is the V of alpha 01010001. See, so like previous derivation, we put first bracket. So SR42 I have used. In fact, we have chosen this example in such a fashion, both the matches, both match. So initially we are given, that syntactic derivation. Now we are giving semantic derivation. If we check side by side, they'll match. So here, I have used SR42. From SR42, we can check that I can put star here, because SR42 it is 0101 and 0101 if we consider it's a beta, and 0001 we can consider it as gamma. In this way, and 0101 can be seen as 01 star 01. Okay, so in this way you can see that then I have used the SR2, then again SR2, SR1, and I have used the definitions, okay, of sigma here, and in this way I have written some steps, and after writing the steps, I can see that we can able to reach that 00001 and then 50, which we wanted to test whether from the given string we can reach to the final string. So that this is a derivation. So we can say that from V alpha we can get V beta. So this is a semantic derivation. So one theorem, and this is an important theorem of our work. So it says for any WFF alpha, V alpha is reducible to V beta, where beta is a WFF in normal form. You take any alpha, and if V alpha is there, and V alpha is always reducible to V beta, and beta is normal form. So the formal proof is not given here. You can test that. An example I have given, that 0101001. I can reduce ECA. Next, we show ECA as model of LCA. A model is an interpretation of a formal logic. So we want to show that the ECA, elementary cellular automata, they are also an interpretation of our logic. So here ECAs are of finite size, and this is under, we consider periodic boundary condition. So the finite system with periodic boundary conditions. Periodic boundary condition means first cell and last two cells. First and last two cells are neighbor of each other, so it forms a circle. So here, and ECA, it forms, it's a one-dimensional CA. Okay, Okay, it's an array of cells, and each cell is either in state 0 or in state 1. Okay, and each cell uses a 3-input binary function called rule. Okay, and this rule is used by all the cells, and all the cells that are updated simultaneously, right? In this way, we get configurations. A configuration is nothing but a collection of all the states at any given time. Okay, so how what you get from one configuration, it goes to another configuration. That configuration goes to another configuration. So C hops from one configuration to another configuration to another configuration in this way. So consider it's a there is a function, we call it global transition function, okay, which transforms a configuration to another. So there's a brief about ECA. We all know it. So now we can interpret ECA in the domain, in our semantic domain and the logic. So this table shows everything. In this table, there are 3 columns. In the first column, it is the logic, LCA, then semantic domain, and now ECA. See, in semantic domain, we have taken the binary string 0 and 1. Here, 0 and 1 in semantic domain. Its meaning is we are giving meaning to ECAs in the domain of ECA as states of a cell, 0 and 1. And in semantic domain, we get L and R, 2 integers. In case of ECA, they are actually left radius and right radius, and here their specific represents L, R, and RR as 1. Alpha, in case of logic, we call it alpha, and in semantic domain, we call it V alpha. And V alpha belongs to, I consider V alpha that belongs to 0, 1 to the power n, a string of 0 and 1. Its meaning is, in the domain of ECA, a configuration of size n. And PIs, so in case of capital P, it is P1, P0, P1, P2, etc. These are the atomic WFFs. Okay, so here I have taken capital N equal to 6. So we have 6 PIs, so P0 to P5. That the atomic WFF. In the semantic domain, we give this one V1 P 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1. If you check this condition, check this valuation with the condition we have stated before, you see that it matches. So it's a valid valuation. Okay, it's a real evaluation to these PIs. And this is actually, you can see that they are the elementary circuits of our diffusion graph. So semantic domain, in the semantic domain, these VPIs, they're actually elementary circuits of a diffusion graph. Okay, and if I take the PI to the power k and it is VPI to the power k, these are actually the homogeneous configuration, right? They are actually the homogeneous configuration. And okay, you know, it is a very simple one. Then sigma to the power k alpha is a formula. Here sigma to the power k V alpha we interpret in the semantic domain, and this is nothing but shift equivalent to alpha. Okay, and star, alpha star beta, here when R alpha beta holds, this actually V alpha V beta, when R V alpha V beta holds, this actually in EC is V alpha V beta. And here, if in the logic, if it is alpha beta, in the semantic domain it is V of alpha V of beta, again we get the same thing. So V alpha V beta. So in case of ECA, so they are same actually. V alpha star V beta and V alpha V beta, they have same meaning in case of ECA. So if we interpret in this fashion, and we can easily see that the evolution of ECA is nothing but a derivation in our logic. This is our proposition, and for the most important finding of our of this work. So evolution of an ECA is a derivation in the semantic domain of LCA. Okay, so again, proof is simple. I shall not go into the proof. and take an example. Let us consider ECA rule 90. Okay, and this is a diffusion graph. You know that this is a diffusion graph. It is overlapping sequence. It considers, and I have written the next state in this fashion. So 0, 0, 1 here, zero, so from the node 0, 0 to 0, 1, it is overlapping sequence 0, 0, 1, and this next state is 1. So in this way, I have written the next state of I have written the next state, and you can see, you can check. This is actually ECA rule 90. You can see there are few cycles. Say all 0, 0, 0 forms a cycle, 1 forms another cycle, and 0, 1 another cycle of length 2. So 0, 0, 1 another cycle in this way. So temporal rules for the ECA 90, as I've said, in this case we have to define the temporal rules. So we have 6 temporal rules. TR0 for the ECA. So the diffusion graph is interpreted in these temporal rules. See, what is shown in the diffusion graph, that is actually interpreted in temporal rules, nothing else. So TR0, 0 to 0. TR1, 1 to 0. You can check from the graph also. TR2, 0, 1, I'm getting 0, 0. In this way. TR3, 0, 0, 1 to 1, 1, 0. TR4, 0, 1, 1 to 0, 1, 1. And TR5, 0, 0, 1, 1 to 1, 1, 1, 1. So these temporal rules we get from rule we get for rule 90. So obviously in case of ECA there are 256 rules. So 256 for 256 rules will get different 256 sets of temporal rules, and obviously the spatial rules will remain same. Anyway, let us consider, let us show this one evaluation by an example. Say first one, 1, 1. This is one of one configuration of length 14, and these are the next configuration. I know it, so you can check it also. The first configuration is the say initial configuration. Next one is the next configuration, and I want to see whether I can get the next configuration in our logic. Okay, so starting is okay. So I have written one thing, the reverse one. Actually, it will be, I want to show that 0, 0, 4, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1. This is the configuration, and from that configuration, I want to reach to the other configuration. This is 1, 1, 1, 0, 0, 1, 0, 0, etc. So probably it is written in the reverse way. Okay. Anyway, so here the configuration is given. Okay, so then I systematically apply the rules. First SR42, then I introduce star. Okay, then again we break the substring. And what is the purpose of this one? See, in case of semantic derivation, our purpose is, and all kind of, in fact, all kind of derivation, our purpose is to purpose of using special rule is to identify the atomic WFFs in between them. So in this way, here you can see, finally we get a formula which consists of only, which consists of some atomic WFFs. So here 1, 1, you can see in between, like we can get this one atomic WFF you can get. Once we get the atomic WFF, then we can apply temporal rules. Okay, so then we use temporal rules, and then we, as usual, we apply some elimination rules, and finally we reach to 1, 1, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0. So therefore, from the first configuration which is given here, from that configuration I have to reach the other configuration. So it is a derivation from our previous definition. We get that this is the derivation, and importantly, this also the next configuration is also In next, the final one, final string is actually the next configuration of the first configuration. So it proves that evolution of an ECA is a derivation in a logic. So we are about to end. So it's a final result. So any one-dimensional binary CA is actually a model in the semantic domain of LCA. This is our. I have shown only one example. I have shown the example of ECA, but it is true. You can show it is true for any one-dimensional binary CA that this result holds. So the proof is there, but again, the proof is not stated, not given yet. So now let us conclude. Now the question is this construction applicable to non-binary CS? What we have shown when you have started, there is no question of binary system. Then we have interpreted the logic in the domain of 0 and 1 only. So question is this construction applicable to non-binary CS? Or can it be extended to infinite CAs? The CA is classically the infinite, but here we have considered the finite case only. Can this result be extended to infinite CAs? We believe the answer is yes. So although it is our future work, we want to do it in our future, but we believe it's possible. It's not very difficult to extend in the direction. Now, if it is asked, can this construction work for 2 or higher dimensional CAs? The answer is no directly. So direct answer, if you asking the direct answer is no. So because we have targeted only one-dimensional CAs, and nature of one-dimensional C and high-dimensional C, they're different. There are many differences. But we have some question. I mean, at some point, maybe this idea may be extended. Maybe we need some modification, and if you could do that modification, maybe it's applicable. It will be applicable. I mean, we'll be able to handle the two-dimensional or higher dimensional CS. And that's all. Thank you. Shall be happy to hear questions and
Thank you so much, sir.